Black holes are probably one of the most popular cosmic topics.
What is it about them that attracts people so much?
Undoubtedly, they generate such interest, not least because their modern descriptions and properties attributed to them by scientists are so unlike anything we can encounter in everyday life. They are more akin to something from the pages of science fiction, and yet they are real. At least that's what the majority of scientists believe. One of such super strange aspects of black holes is, of course, the singularity that may exist at their center, a point of infinite density, an area where the known laws of physics break down and where space and time swap places.
But we are accustomed to hearing that the singularity is hidden behind the event horizon of a black hole. But what if there could exist a naked singularity?
I've had several videos covering various aspects of black holes, starting from how we came to know about their existence in the first place, to exploring some alternatives to black holes. Of course, I talked about singularities as well, although usually not in such detail. Today let's talk about singularities themselves, about cosmic censorship and naked singularities, what they are, how they appear, and whether they can exist.
My name is Andrei, and this is Cosmos Elementary. Before diving deeper into the naked singularity, first let's take a look at the singularity in general, or more precisely at singularities, because the concept itself is quite broad and applied in a variety of fields.
When we hear the word singularity, we probably immediately think of black holes or the state of the universe before the Big Bang. However, very often this word is used in a completely different context. But at the very least, many have probably heard of the so-called technological singularity. That's the one where, in the future, artificial intelligence may start self-improving uncontrollably, a superintelligence might emerge, and it may not end well for us.
First and foremost, let's look at mathematical singularities, but we won't delve too deeply into this. Singularities in mathematics refer to a point where an object exhibits strange or unusual behavior, or a point where an object becomes undefined.
If we open the dictionary definition of the word singularity, one of the meanings is unusual behavior. It also means something singular.
But what does that mean? The point where an object becomes undefined. There can be many types and examples of mathematical singularities. But let's look at the one example that is often cited, the singularity of this function.
Let's plot the graph of this function. Write 1 divided by x here. The graph appears if x equals 1, dividing by 1 again equals 1. And on the graph, it's right here. But if x equals 1/2, it would be 2. And if x is 1/10, it would be 10. At 1/1000th, it equals 1000. It seems like the graph coincides with the axis, but if we zoom in, we'll see that it's not actually the case.
So the smaller value of x, the larger the resulting number, and the closer the graph gets to 0.
We can even put 1/1,000,000,000th an x, and the number on the graph will be 1,000,000,000. It turns out that if we take smaller and smaller fractions, the number will increase, but the graph will never approach 0. The smaller the x, the larger the result. The number starts to approach infinity.
But what if we intentionally put 0 into the function? We just established that the graph will never reach 0. Since the closer the number is to 0, the larger the result, it seems logical to say that if x equals 0, then the result is infinity. However, infinity poses a problem. Here we basically divide by 0, which is a no-no. Mathematicians don't really like infinities very much, so here it is often said that in 1 divided by x, the point where x equals 0 is undefined. And what did we just define as singularity? a point where a mathematical object is undefined. So for this function, x equals 0 is a mathematical singularity.
Singularities are not necessarily associated with infinity. There are different types, such as removable coordinate singularities. These are, for example, singularities that are undefined in certain coordinates, but if you choose a different coordinate system, the singularity disappears. To form some understanding, the example with the function 1 divided by x is sufficient for now, so we have this function with a singularity. Now what?
Well, not much. While we're discussing a mathematical abstraction, there isn't much of a problem. But when such undefined points arise in the real world, that's where the problems begin.
Exactly such a problem is posed by black holes with their singularities at the center, which seem to be not just a mathematical abstraction, but to actually exist. Or do they? When we talk about gravity and singularities, we immediately think of Einstein, Schwarzschild, Penrose, but something similar can actually appear even in the framework of classical Newtonian mechanics. Here is the formula for the gravitational force from Newton's law. The force is equal to the gravitational constant times mass 1 and mass 2 and divided by the square of the distance between the two masses.
We have two objects, and how strongly they attract each other depends on their masses and distance between them. Obviously, the closer they are to each other, the stronger the gravitational attraction.
For example, let's use the Earth as the first mass and the person with a mass of 60 kilograms or 132 pounds as the second mass. If the distance between the masses is 20,000 kilometers, the force acting on the person is 59.77 newtons. At a distance of 15,000 kilometers, it becomes 106 newtons. At 10,000 kilometers, it is 239 newtons.
We can go on further. The shorter the distance, the stronger the force. But what happens when the distance between them becomes equal to, well, 0?
Well, Wolfram gives us infinity newtons. Does this mean we have infinite gravity? Essentially, in this formula, we find ourselves dividing by 0. We encounter a situation similar to the example with 1 divided by x. A singularity arises.
Certainly no singularities occur when we reduce the distance between two masses to 0. We stand on Earth, but infinite gravity doesn't crush us, because the distance to the center of mass is still 6,371 kilometers or about 4,000 miles.
And even if we find ourselves close to the center of the Earth, not all of the mass will be concentrated beneath us. A significant portion of the mass will in fact be above us, and certainly there won't be any infinite gravity.
The problem and the actual zero distance would occur only if all of the mass were concentrated in a single point. And this description closely resembles the conventional understanding of a singularity in a black hole.
We have theoretical predictions that suggest objects like black holes could exist. Furthermore, we have a series of observations indicating that in the universe there are very massive and, at the same time, very compact objects. Theoretical predictions align quite well with the observational data, and as of today, the best explanation for these objects is black holes.
This doesn't mean they definitely exist, but currently this is the best explanation we have. And they come with their own set of problems, and some of which are quite serious.
This includes the paradox of information loss in a black hole, which I covered in a separate video quite a while ago.
And singularities? Well, in a separate video about the alternatives to black holes. All of those alternatives tried to address these problems, including getting rid of singularities.
When describing a black hole, it's often mentioned that it has, first of all, an event horizon, a region in space at a certain distance from the black hole's center, a kind of a boundary. Once something crosses this boundary, even light cannot escape. Just beyond the event horizon, there is nothing special, just empty space. However, all the mass of the black hole is concentrated at the center. at a point of infinite density, the singularity. Here, there are a couple of caveats though. Firstly, this is the description of the simplest model of a non-rotating Schwarzschild black hole. Secondly, as I mentioned earlier, we're not even 100% sure that black holes exist. However, if they do, what's inside the event horizon is something we have absolutely no direct means of knowing. So all discussions about what is inside the event horizon, including the singularity, are theoretical and stem from solutions to Einstein's equations. As I mentioned, Schwarzschild solutions were for the simplest case, a spherically symmetric, non-rotating mass in a vacuum.
Originally, Schwarzschild solutions had actually two singularities, one a point at the center and also a ring at a certain distance from the center. The second singularity turned out to be a coordinate singularity and not a true one like the point in the center, and the second singularity became known as the event horizon.
In general relativity, gravitational singularities still lack a clear-cut definition. However, they are undeniably peculiar entities. Sometimes in discussions about singularities it is suggested that space-time itself breaks down in these regions.
These are kind of places where the words where and when essentially lose their meaning. Some kind of edge of space-time. How can space have an edge? A singularity can be identified by particles in threefold. A particle travels through the universe in a straight line and then it simply and suddenly disappears, vanishes from existence.
It's like imagining that this sheet of paper is a two-dimensional analogy of our universe. In theory, it should extend infinitely in all directions, and the particle's path would look like this, but then suddenly, hop, and the particle encounters a rupture.
I came across an analogy with paper for a certain type of singularity, a conical singularity.
Just on a sheet of paper, the particle or a line can continue indefinitely, but if you turn it into a cone, the straight line stops at the apex. It's challenging to envision the same thing in three-dimensional space, which is why we use the two-dimensional analogy. In illustrations, space is often depicted as a grid, again, often in the form of a two-dimensional analogy. Under normal conditions, these imaginary lines continue infinitely. It may only bend under the influence of mass, as shown here. But in the case of a singularity, they converge at one point and literally come to a halt. It's like an end or edge where space and time cease to exist.
To form a black hole, perhaps with a singularity in its center, we need to compress certain mass to a specific Schwarzschild radius. The only realistic scenario where we can envision this is through gravitational collapse. If there is a concentration of mass, matter attracts matter, and it can collapse if there are no opposing forces.
In the case of stars, as we know, for much of their lives, stars don't collapse because the gravity trying to compress them is counteracted by the outward pressure generated by nuclear reactions in their core. As long as this balance is maintained, the star exists. But when the balance is disrupted in a massive star, it collapses. In stellar remnants, there are also processes preventing them from collapsing further. In white dwarfs, it's degenerate electron gas pressure, and in neutron stars, it's degenerate neutrons gas pressure. But when a certain threshold is reached, nothing can resist gravity anymore. Gravity ultimately triumphs and the object collapses into a black hole. In neutron stars, the density is unimaginably high but finite. However, in the case of a black hole, it is said to have infinite density. Density is mass divided by volume. And in the case of singularity, it becomes infinite, not because the mass is infinite. The mass remains the same, but because this mass must now be concentrated in an infinitely small point. In other words, we again divide the specific mass by zero. Again, an undefined value, a singularity. Along with infinite density, we also have infinite curvature of space-time. By the way, the singularity in a black hole is not necessarily a point. Roy Kerr developed solutions to Einstein's equations for a rotating black hole, which theoretically should be more complex than the Schwarzschild model and also more realistic. In the Kerr model, the singularity is no longer a point, due to rotation. It forms a ring. This is known as a ring singularity.
The crucial question remains: are singularities in general relativity just some mathematical artifact, or do they actually exist in reality?
For a long time, the first option was considered. Early solutions explored spherically symmetric mass. The argument was that in reality, such a perfect case is unlikely, and perhaps singularities are just a side effect that arises in solutions when assuming spherical symmetry. In 1965, Roger Penrose wrote his famous paper in which he described gravitational collapse not for an ideally symmetric spherical body. As a result of this research, he was awarded the Nobel Prize in Physics. So he demonstrated that singularities must arise during collapse. One might think that he proved the existence of singularities in black holes, but it's about something else.
He showed that they should emerge in the general theory of relativity.
Despite the theory being highly successful at describing numerous phenomena in the universe, making successful predictions, it is evident that it is not complete. Singularities in black holes serve as another illustration of this incompleteness. To better understand what is happening, we need a more advanced theory, the theory of quantum gravity, which has not yet been constructed.
But another consequence of what Penrose wrote was that singularities could emerge even without event horizons. In other words, general relativity allows for the existence of naked singularities.
So it's the one thing when this strange thing is hidden behind the event horizon, making it impossible for us to know what is actually happening there. Maybe space-time is being torn apart there, but at least we cannot see it. But it can also theoretically be visible to everyone.
Therefore, in 1969, Penrose himself formulated a so-called cosmic censorship hypothesis. The essence of it is that the universe should not allow naked singularities to appear, and singularities should be concealed behind the event horizon. This principle acts as a guardian, preventing general relativity from problems posed by singularities.
More precisely, if the principle holds true and we do not directly encounter singularities and they remain hidden from us, the general theory of relativity continues to function and accurately describe the rest of the universe. It does not require modifications.
It's not a formal law, rather an idea, an initiative for further exploration. In other words, that this principle, this hypothesis was formulated by a human shouldn't really bother the universe that much. If the universe wanted to throw a party with blackjack and naked singularities, it would do so. But the key word here is if. What if they do exist and the universe allows for existence of such weird entities? Could naked singularities actually exist? So naked singularities are the same problematic entities, but they are not hidden behind the event horizon. In other words, all of the physical weirdness that occurs around them is exposed to the entire universe to see. And that is a problem.
Our laws of physics break down near gravitational singularities and are unable to describe them, making it quite challenging to speak about their properties and what they would actually represent in reality if they existed. Unlike the singularity with an event horizon, where all paths lead to the singularity, in the region of a naked singularity, particles and light can escape from this region. One form of a naked singularity could be a white hole. Essentially, it is the opposite of a black hole. While a black hole attracts matter, the white hole in theory propels it outward. And also, it moves back in time. It is said, naked singularities, if they exist, would be holes in the fabric of reality that not only distort space-time, but also shatter the laws of physics wherever they appear, leading to a catastrophic loss of predictability.
But this is on paper. For decades, scientists have debated whether naked singularities can exist. And there is a substantial body of scientific literature on this topic.
The Astrophysical Database yields almost 2,000 papers on the topic of naked singularity, and as we can see, their number is increasing, especially in the recent times. The cosmic censorship hypothesis is not an exact mathematical solution that prohibits the appearance of naked singularities. Some scientists are indeed attempting to challenge this principle and find models and solutions in which naked singularities could arise.
Typically, scientists create models with specific parameters. And for some time, models were created where naked singularities did appear. But these were models of five-dimensional universes. Our universe is not five-dimensional as far as we know, but the existence of such universes doesn't contradict physics.
However, not long ago, scientists managed to create a model of a universe with 4 dimensions, 3 spatial and 1 time dimension, just like our universe, and in this model, naked singularities could indeed arise. But this model of the universe still differed from ours. The virtual universe had a different geometry, or roughly speaking, a different shape. Again, the general theory of relativity allows for universes with different geometries.
So in some works, models that manage to recreate naked singularities become closer to our universe. However, at times, researchers have to set very specific and not very realistic set of parameters and conditions for naked singularities to appear only in those scenarios.
On the other hand, there are also studies suggesting that under certain parameters, such as having gravity as the weakest among the 4 fundamental interactions in a given universe, the cosmic censorship hypothesis works, and singularities are always hidden. In our universe, gravity happens to be the weakest. In general, there is no consensus on this matter, and theorists continue to work on this issue.
By the way, how could a naked singularity even appear in the first place? Well, again, here we only can make some assumptions.
In general, we're discussing gravitational collapse, for instance, that of a star, as in the case of a regular black hole. However, under specific conditions, if the resulting black hole rotates very rapidly, in such a black hole there may be not 1, but effectively 2 event horizons. And the faster the black hole rotates, the closer these horizons are to each other. When a certain rotational speed is reached, these 2 horizons can meet and reveal the singularity at the center.
But okay, models, theories, and calculations aside, maybe we could just go and try to find a naked singularity somewhere in the universe. Well, we could try.
Indeed, we do not observe black holes directly, but rather detect them by observing matter in their accretion disks which surround them and emit radiation, and also through other interactions with visible matter. The calculations made by the authors of this paper indicate that the radiation from an accretion disk around a naked singularity would differ from that around a regular black hole of the same mass. Essentially, the material around a naked singularity would emit more strongly. In theory, if we encounter an object that could be a black hole, but its radiation is much stronger than expected for its mass, it could be a naked singularity. However, it's important to understand that this idea is built on assumptions, and other factors could also be influencing the observations. Externally, black holes and naked singularities with accretion disks can differ. In the case of a naked singularity, there may not be a photon sphere. Additionally, there could be a complex structure of bright rings present. The radiation from such a structure could theoretically be detected. However, as of now, no signs of naked singularities have been found anywhere in the universe. There is currently no consensus on whether naked singularities can exist. What they do emphasize is that our understanding of the structure of the universe is far from complete. As usual, much of it comes down to the fact that we currently lack a so-called theory of everything. Singularities, especially naked ones, represent situations where our best contemporary theories break down and cannot describe what happens in certain conditions. Certainly, if we ever managed to find a naked singularity in reality, it would be truly extraordinary. It would be a specific example, not hidden behind an event horizon. not somewhere in the distant past during the early moments of the Big Bang, but right now in the observable universe, that would indeed push the boundaries of our understanding. And also, such a discovery would shake up the scientific community and potentially lead to a deeper understanding of the inner workings of the universe.
Thanks for watching. Links to all of my information sources are, as always, down below in the description. And if you enjoyed the video, leave a like, comment, subscribe for more videos in the future, and feel free to share this video with some of your friends on social media or somewhere else. Thank you, and bye.